excuse Professor Alatov to speak about variation of forcing on method for the confinality of S less than S.
Well, thank you very much. Thanks for inviting me. Put a little testimony there. My great honor and greater pleasure to be here celebrating Gary's. I thought we were celebrating Gary's enormous impact on topology. Of course, Gary has many results. Many of them have been published, but I know of one that wasn't published. We were at Roland, Missouri, I believe it was, and we sat down for lunch with many people. And it was cool. It was quite cold that week in spring college. And I took off my jacket, so I'm about to show you a prop here. So I took off my jacket, and then my shirt revealed. You probably can't read it at that. It says, "Last clean shirt." And Jerry said, "Who's sitting beside Ellen tomorrow?" That cracked me up. But I brought spares this time, so sit beside me tomorrow. All right. Well, this is just a great celebration of a very fantastic individual. And I hope to contribute a little bit by talking. I had some trouble trying to decide what to talk about, but this sort of method, so I have this result. I didn't write the test, the co-authorship with Saharan Shalah. Most of them are certainly his ideas in the paper, but yes, this result is joint work with Saharan Shalah. And I thought, well, maybe I should talk about that. And then it turned out that just several different things coalesced recently that I can make the talk about the forcing method rather than just simply this result. And I don't intend to go into really great detail because I probably certainly couldn't. So I'll begin by talking about the splitting number. S is the splitting number. And I just want to define S in a slightly unusual way. Just for the purposes of explaining some of the proof. So S is the maximal cardinal, such that every Boolean subalgebra B of the power set of omega, of smaller cardinality than S, that you can find an ultrafilter on B that has a pseudo-intersection. So no family of size less than S is splitting, is equivalent. And what is a pseudo-intersection? I'm sure I don't have to define that, but I decided I would. So anyway, I won't even read it, right? So the pseudo-intersection of the ultrafilter on the subalgebra is an infinite set that is mod finite contained in every member of that family. And I might mention later in the talk, for an ultrafilter, this pi character of an ultrafilter is the minimum cardinality of a pi base for the ultrafilter in omega star. And I might mention, Peter's been talking here, is the cause of some of the overlap with this method that I've been experiencing. The pseudo-intersection number for an ultrafilter is similar. So the pseudo-intersection number of an ultrafilter is the minimum cardinality of a subset of the ultrafilter that does not have a pseudo-intersection. Need not be in the ultrafilter, but it doesn't have a pseudo-intersection at all. Okay, so just a couple of cardinals there. And so we want to talk, to begin with, about the splitting number S. And so we want to get S equal Aleph sub omega 1. All right, so S will be singular. We want S to equal Aleph sub omega 1. So in order to get a model where S equals Aleph sub omega 1, we've got to make sure S is bigger than every Aleph sub alpha for alpha less than omega 1. We'll start with a ground model of GCH and force, and we'll do a CCC forcing. I forget to say it, every coset is CCC today, for the rest of today. Tomorrow they might not be. Okay, so here is a poset that's used quite a lot. It's a great poset. Michael Rushat uses a labor style poset. So a free filter D on omega, you can define this poset without the filter being free. For a free filter on omega, the poset L of D consists of all trees. So the poset consists of trees for convenience, strictly increasing functions, finite functions. Right? The domain is is an integer and the range is in omega. So just strictly increasing finite sequences of integers, a tree consisting of them. And it has a root node, or stem I call it here. So you have a minimal node where it starts branching. And once it starts branching, it never stops. So every node above the stem is branching, and it has to branch filter at large, right? So the set of immediate extensions of a member of the tree, that set of integers has to be a member of that filter. Okay, so that's the family of conditions, and then you extend a condition simply by finding a subtree. So stronger condition is simply a subtree. And this coset will do exactly what I said the definition of S was. This coset, if you take a generic filter for the coset L and D, and you follow the stems, you get a strictly increasing sequence of integers, the range of the functions you get, and it's a pseudo intersection for the filters. So L of D adds a generic sequence. I'll call it Z dot. So Z dot is the sequence of the integers chosen by the stems. And it is, it's just easy to check that it's forced to be a pseudo intersection of the filter D. And this is a remark more than an important property, right? So, and it just, you can notice, adds a dominating function. This function n, going to case of n dot, ends up being a dominating function. A lot of what we have to worry about is, as we force, what else do we get that maybe we didn't want? So we definitely want a pseudo intersection for D. We end up getting a dominating function. And just a remark that the cardinality of that poset, it's a big poset. It has cardinality C. But if you look at the filter, and it turns out if the filter has small characters, so if the filter has small characters, then it will preserve, for example, kappa tau. So if you have a mod finite descending sequence of length longer than the character of the filter, you will not add a pseudo intersection to that particular tau. So you will add one to D, so this is, character of D, so you think of D as smaller. So that's kind of good. So it preserves kappa towers, so maybe it has a chance of preserving, and it does, preserving a family that is splitting. All right, so that'll be a tool for getting S to be at least aleph sub alpha for every alpha. And then we are now also worrying about how to keep S from getting too big, right? So we want S to be at most aleph sub omega 1, but at the same time bigger than every aleph sub alpha. So this simply adds aleph sub omega 1 many Cohen rings. So I'm going to write it as a doubly indexed thing, P sub 0 omega 1 looking to the future. So P sub 0 comma omega 1 is union over alpha less than omega 1, and think of it as at level alpha, you add omega sub alpha many Cohen subsets of omega. And just for reference later, so for each first coordinate alpha, second index C, let C range to omega sub alpha. That's supposed to be, that's okay. This is wrong, right? This is just supposed to be omega sub alpha. Sorry about that. So omega sub alpha, there's a name for the Cohen ring, the next Cohen ring. Right? So for every alpha, you have omega sub alpha many Cohen rings, and there we are. And okay, so we're going to get to the method in a second. So by induction on gamma, and gamma is going to range very large. And so now this first coordinate 0 is going to become actually aleph sub omega 1 plus 1. We got to go as far as 2 to the aleph sub omega 1. So we go out very large, and we build a sequence of CCC posets, bigger and bigger and bigger CCC posets by a finite supported iteration. And then as we go along, when we get to stage gamma by some kind of diamond or just an enumeration, we look back at the poset that we built so far, and we choose fewer, so aleph sub alpha many names, and that we have to find a filter on this sub-algebra of P omega. We have to find a filter on that, and we have to give it a pseudo-intersection.
The B gamma omega 1 is in red, in which model? In the ground model?
Ground model, yeah. I'm just discussing how to build a poset, right? So P0 omega 1 is that, and then we're going to build bigger and bigger and bigger posets, all in the ground model. And so this is a family of names of subsets of omega. And so what we'll do is that we use that, so somehow, and this is the somehow, we pick a name of an ultrafilter on that Boolean algebra, and at the next stage of the poset, we add a pseudo-intersection to that filter, thus destroying that this family is splitting. And that's how we get B gamma plus 1, comma omega 1. What's the purpose of comma omega 1? We'll get to that. Yeah.
The later process is not CCC.
Yes, it is. I'm glad you asked that. I should have said so. Because it all have, as long as the stems are the same, they're compatible because it's all the same filter. Yeah. So that's, I did say every poset was CCC.
Yeah, that's why I asked.
Okay, so this going back doesn't seem to. Oh, there we go. Okay, so that's our next poset, is to add a pseudo-intersection as we promised to do. We have to add pseudo-intersections to every small subalgebra. And, looking promising, right, we noticed that, as we said a minute ago, well, I said about towers, but it's also true about these generic splitting families. So that as long as the character of B gamma, which is bounded by the cardinality of B gamma, as long as the character of D gamma is smaller than omega sub alpha, this subfamily of the family of coordinals we added, it will preserve its splitting. Meaning, if it's splitting so far, it will be splitting in the one more step. So it looks promising that as long as this is small, it will preserve that this is still splitting. But here's where you run into a big problem, right? So what's going to happen? Let's say at stage alpha less than omega 1. Well, there's a small subset of names, and then generate the Boolean algebra by that small subset of names, smaller than omega sub omega 1, alpha sub omega 1. And so this poset in this coordinate will add a pseudo-intersection perhaps to that family. And then we get to stage omega 1, and that family there, Z alpha, alpha less than omega 1, is fewer than alpha sub omega 1 many, and then we might add a pseudo-intersection to that, and then we completely ruin the whole game, because we ended up adding a pseudo-intersection to the whole thing, and we broke our hope that S will remain alpha sub omega 1. So we have to get around that problem. Okay, so that's where this method comes in, how not to fail, how to preserve. In essence, we've seen how to get S up to alpha sub omega 1, how to preserve that S is at most alpha sub, let's equal alpha sub omega 1. So it's going to be what I'll call a two-matrix strategy, hence the two subscripts. So clearly, the first coordinate poset, P0 omega 1, can be thought of, written, as this increasing chain of CCC posets, right? So at level alpha, we added omega sub alpha many more coordinals, and up we go. And this notion is going to be extremely important. That if alpha is less than delta, less than omega 1, there's nothing magical about omega 1 here. Then this notion of being a complete subposet, right? So the initial segment, P0 alpha, is a complete subposet of the bigger posets. And what that means, you can write it down in terms of antichains. Every maximal antichain of this poset, it remains a maximal antichain of the bigger poset. And what that consequence in terms of generic filters is, if, so in general, when P is a complete subposet of Q, in the forcing sense, it means that a generic filter for Q, when you intersect it with P, is a generic filter for P. So the forcing extension by Q is a forcing extension of the forcing extension by P. The forcing extension by P is an intermodel to the forcing extension by Q. So we want to, just at this moment, look at it, the 0, comma lambda. So the two matrix, first coordinate 0, last coordinate lambda, but there are only two coordinates. What am I talking about? Well, we'll get to that. So suppose, you know, we did that finite support iteration of building P lambda omega 1. Talked about all the gammas less than lambda, and we went up to lambda. Lambda is probably, as I said, aleph sub omega 1 plus 1 here. And what if it could be written as a complete subcoset increasing chain of length omega 1. So what if, so we know that P0 omega 1 is this increasing chain. What if, when you get to the end, it's this increasing chain, and what if the increase, the P lambda alpha is add the first alpha mini coreals and then do a bunch of labor cosets along the way, and in such a way that you keep the characters small, keep the characters